Sure. Good morning, everyone. It's a pleasure for me to be joining the conference. I'm hybrid today. I'm joining from Geneva, Switzerland, but I definitely hope that I'll have a chance to attend another IQT conference physically soon. So since I'm joining remotely, I will only benefit from partial entanglement, but as physicists know, there's entanglement is not black and white. It can also be partial, and even partial entanglement can be beneficial. Before I start, I'd like to thank the organizers. The pandemic is still very much something that we live with. Even though some restrictions are being eased in many locations. But I think that for a very fast-moving field like quantum technologies, like our field, it is so important to have such events, and it's great that they can take place, and hybrid mode is also very good. So the title of my talk today is From Quantum Communication to the Quantum Internet. And IDQ is probably one of the first companies that has been active in quantum communication. Company was founded in 2001, so more than 20 years ago. And we were the first company to bring QKD to the market. And what I'd like today is to look a bit at the past of quantum communication, at the present of quantum communication, in order to kind of see what the road ahead is for us. And so if I start my talk, I think, I think, there can be essentially four steps that can be defined for quantum communication to the quantum internet. Of course, we heard that the principles of quantum technologies were invented about 100 years ago by a small group of physicists, but the second quantum revolution really started in the 80s with the invention of BB84 by Charlie Bennett and Gilles Brassard. And then this idea of quantum communication became reality in the first applied research in the 90s. And that led us in the year 2000 to the first applications of quantum communication. And essentially in the 2000, we started to see applications of single QKD links. That's the first step that we can define. I think a second step started about 5 years ago when various people around the world started to connect several QKD links into networks to enhance the possibilities of applications. These networks are still to some extent regional or maybe national, but do not cover global scale. And the next step, maybe 2-3 years from now, in the middle of the decade, will be to have quantum networks that cover globally the global scale. And the final step of this road will be the quantum internet. Hard to predict a date, but let's say in a small decade from now. So what I'd like to do is review these four steps with you today. And if we start, QKD link, so what is it? QKD is about exchanging single photons, quantum objects, single photons through a quantum channel, typically an optical fiber. And the idea is that quantum theory will ensure that any attempt at eavesdropping can be detected because it will leave a trace in the form of errors in the sequence that's being exchanged. What's nice about this is that you can define or prove the security of this technology based on the laws of physics. That's what physicists say, and a few other assumptions. Of course, the fact that the device performs according to the model. But that's, I guess, something that is always the case in cybersecurity. The idea is that you can use this to exchange cryptographic keys, and these cryptographic keys can be used to ensure long-term security of data. And what's interesting is that the security being based on physics, it does not require computational assumptions. And in this sense, it makes the solution secure even against new threats such as quantum computing. So to my knowledge, the first commercial application of this kind of technology in a single point-to-point link took place in 2007 when the IT department of the Geneva state in Switzerland used this technology to secure communication between the central vote counting station and a data center in an election, federal election held in Switzerland. So that's the first application, which brings some benefits in terms of security, as explained, but there are still some improvements that could be needed. First of all, it's only point-to-point, and I'll mention a typical application of these single QKD links. And it's also in the early days, it was also necessary for end user to own and operate their systems, which is, of course, goes a bit against the trend now of as-a-service type of IT systems. And maybe a final point is that it had to be locally managed. You had to be on site to manage the equipment. The typical application of this first kind of QKD links was essentially to connect data centers, as I explained. So typically in a case where a main data center in a headquarter of an organization was connected to a remote data center or disaster recovery site, and the data from the main data center was sent across to this disaster recovery site to avoid loss of data and to guarantee business continuity. And this approach was based on a hybrid approach where symmetric cryptography, traditional cryptography based on symmetric keys, was used to secure the data using keys exchanged by QKD, and these keys being secure against all computational threat could provide long-term security. So, of course, there's been many improvements since the year 2000 when this technology was first used. Devices have become smaller, reach has been longer, etc., etc. But essentially, the functionality has remained unchanged, point-to-point key distribution over an optical fiber link. And now the second step, the step of quantum networks, again started 5-6 years ago. It's a bit hard to say, but the first deployments took place 5-6 years ago. And the idea is now to combine multiple QKD links into a single network. And that's a natural thing to do. QKD links are physical layer technologies, so they remain point-to-point. But if you can add an additional layer on top of them to manage several of these links together, you can build networks and get more functionalities because you can connect multiple sites. Something that also happened in the traditional networking world. So in this kind of use cases, and I'll show a few of these use cases, users located at the node of the network can then get a key, end-to-end key, with any other nodes of the network. And this kind of networks also allowed the development and the emergence of as-a-service types of offering for QKD, where a user can connect to a network without owning the devices, but get keys from a network operated by another entity. Now, as we will see, these kind of networks are based on something called trusted nodes. So they're not end-to-end quantum, but at every of the nodes, the quantum objects, our photons, get detected and then recreated, which means they become classical. And so these nodes must be trusted and be secure because information keys could be available in these intermediary nodes. Of course, this can be achieved using some kind of physical security, which already exists. The second point is also that global reach for these nodes is still challenging. These networks are typically based on optical fiber networks, and they are regional and national in scope, but do not cover global scales. If we look at a first example of such a network, this is a project that we did with BT and Cambridge University in the UK, where the idea was to connect two remote locations, BT's Adastral Park campus and Cambridge University. And this is a very simple example of a network. It's a linear chain in a sense, that can be used to extend the range of QKD by putting intermediary nodes. And so this project was deployed a few years ago, over 125 kilometers of standard optical fiber provided by BT, and all the signals were combined into a single fiber. So that was a first type of example. I'd like to mention a second example that is currently being deployed in Korea and is a very, very complex network. This is a project that is delivered by SK Broadband, which is a telecom company in South Korea, and based on IDQ equipment to secure the converged network of the Korean government to connect sites all over the country. The idea is that all public or all civilian administration in Korea are going to use this network to connect their sites. There are 48 government organizations connected through this network that covers some 2,000 kilometers. And what you see on the right of this diagram, it's not very clear, but it's supposed to show, you can imagine the peninsula of Korea, of course covering South Korea, where in orange you see regional offices of SK Broadband, this telecom company, where QKD equipments are located. The gray circles or semicircles represent the QKD links, and the blue triangles are the locations where government offices are located and connected to this network. And what can be seen here is that what comes on top of these QKD links to build networks is a layer of software that actually manages all these links and can be used to provide this security and this end-to-end functionality in order to obtain encryption keys between any two nodes. This is probably the most complex, or one of the most complex networks that are based on QKD and being deployed in the world. Finally, of course, I should also mention a project where we're not involved, but it's what's happening in China, where I think 4 years ago, the first large-scale quantum network was deployed, connecting Beijing to Shanghai, with several also metropolitan area networks along the way. And this really was probably the first large-scale network being deployed, and it was also probably a wake-up call for other countries to start looking at QKD technology seriously. Now, this network, Beijing-Shanghai, this is all fiber-based, but now how do we go to global scales? And this involves still trusted nodes, but trusted nodes based on satellite QKD links. The idea is that instead of having optical fibers, you can have free space links between a satellite and a ground station. And then the satellite will exchange a key, for example, with a ground station in Europe in the morning, and then will move, and a couple hours later, the satellite could be over a different ground station on a different continent, and will then be able to bridge, in a sense, low or regional networks based on optical fibers. This has already been demonstrated, again, in China, but more from a scientific point of view. The satellite that was involved was very complex and expensive, and now there are numerous startup and projects that have been recently launched to replicate this type of result, but to offer a service based on cheaper, smaller satellites, so that it can be scalable and offer and be deployed really for end users. It's hard to really know, how long it will take, but given the level of effort around the world, I think that in the next 3-4 years, we should see the first services becoming available and based on satellites. Now we'll have global networks, but nevertheless, they will still be based on trusted nodes. Of course, a satellite is a bit more difficult to reach if you want to, let's say, open it, attack it, and retrieve keys that pass through it. But nevertheless, it is still a trusted node. And the idea would be to now go to the next step and see how we can really build an end-to-end quantum network. And that's what people call the quantum internet. Of course, the quantum internet brings two very sexy concepts together, quantum and internet. I think, it probably means different things to different people. We still don't really know what it will be, but what we know is that there are some building blocks that are necessary and that don't exist yet. In order to do this, this will be the first application, or one of the first applications of entanglement to provide long-distance communications. You can see on this slide a diagram where two entangled pair source would send photons in two directions, and in the center there's a Bell state measurement which uses a non-classical Bell state, not one based on the Bell as we heard at the beginning of this presentation. And this Bell state measurement would allow to provide to entangle the photons that go in opposite direction and that have never interacted before. And this is one of the building blocks of the quantum internet, or also sometimes known as quantum repeaters. So we need many components for this. It's still difficult science, and so it's still important to work on this with a scientific mind. It's not pure engineering, I guess, in order to improve the efficiency of these building blocks, whether they are entangled photon pair source, quantum memories, Bell state measurements, etc., etc. So these components must be improved. They've all been demonstrated, but not all parameters can be optimized at the same time. And if you look at memories, you can have memories with long storage time, but these memories will have a limited or poor fidelity. The photon that comes out will have some errors compared to the photon that first came in. You cannot have a long storage time and good fidelity yet. But you could also decide to have a good fidelity, but then storage time is a bit shorter. So to take an example, I'm talking to you from Switzerland. In Switzerland, we make watches. It's a bit like if you had a watch that can give you a very precise time, but then the date is not very accurate. So you don't really know what day it is, whether it's palindrome day or not. Or you could decide to have a watch that gives you a very precise date, but then the time is not very accurate. Of course, what you need is a watch that would give you both a precise time and date. And so research is still needed in order to achieve and combine these parameters so that these building blocks can then be used to build the quantum internet. And so the quantum internet, what will it be again? I think there are different interpretations. It's really not entirely clear yet. But what in summary, what we do is that we could say is that today we distribute keys. We distribute classical information using quantum principle and quantum objects. Tomorrow, when we put together these various components, these quantum relays, quantum memories, sources, potentially also quantum satellites that do this, we will distribute entanglement. We will have end-to-end quantum communication. We will, and this will allow many new applications. Of course, it will allow to use this entanglement to produce very secure keys and to not rely on the fact that the nodes are trusted in the middle. But it will also allow to connect remotely quantum computers, to take medium-scale quantum processors and assemble them into a larger-scale quantum computer, and finally also many other protocols that we probably don't even know today, but that will allow new and practical things. And so now I will just finish with a few words on how IDQ sees its role in this building of the quantum internet. As I mentioned, IDQ was founded in 2001. We were the first company in 2007 to demonstrate real world QKD implementation. We've been involved in the implementation of quantum networks since 2017. And we're building this large-scale quantum network in Korea. We are launching new devices to support this development. And I think we see also our role as providing components, the picks and shovels to build the quantum internet, such as, for example, superconducting nanowire single photon detectors, which are a very important component for people working on quantum repeaters, quantum memories, and such building blocks of the quantum internet. Finally, what I'd like to say is that we've recently announced the fact that we are opening in Vienna, Austria, an independent center of competence for quantum communications. The current hubs for research in the field of quantum communications are in Asia, and we've got a foot there, and also in the European Union, where there's this very strong push and investment to build quantum networks. And unfortunately, Switzerland is in continental Europe, but not in the European Union. And we want to play a role still in what's happening in the European Union. And we've set up this center where we will work with partners and customers in the European Union to design, integrate, and support quantum networks, to customize and certify devices, and also to improve and develop new QKD systems and tool blocks based on European IP and technology. And finally, we will also set up manufacturing in the European Union. Maybe I'll finish with one remark. We heard at the beginning of this talk that collaboration is important for quantum. And I'd like to share with all of you one concern that I see in the field of quantum technologies, and it's the fact that many governments start to talk about technology sovereignty and controlling the source of technology. And I think this is the wrong approach. Unfortunately, we're still at an early stage where international collaboration is very much needed. And I hope that politicians and government understand that global problems require global solutions, which come only through international collaborations. With this, I will end my presentation, and thank you for your attention.
Thank you. Thank you so much, Grégoire. And that's wonderful. It's also wonderful to see, let's say, the journey of a company that has come in to the field so early and is developing with the community and with the technology all the time. Very intriguing. Open for questions. You also touched upon the geopolitical issue. People who want to raise questions to Grégoire, one of the CEO, one of the leading companies in this area. There, Julian. Yes, please. You can't see him, Grégoire, but he is there.
Okay.
Hi, thank you for that great talk. You stressed the importance of international collaboration, while you also noted that most of the work for national testbeds is on a national level. So how do you think these two can go hand in hand together?
Well, I think for testbeds are linked to use cases, and to some extent, use cases are local because different organizations and different locations have different needs, and also there's an element, I think, for testbeds of education of users so that they understand how they can use these kind of solutions and technologies. So I don't see a contradiction in having testbeds with a strong national component, but the fact that still it requires international collaboration. And we shouldn't forget that we live in a world where, whether we like it or not, supply chains are internationals. You cannot build a European computer today, or you could not build a Chinese computer or US computer. International collaboration is essential for the development of technology.
Thanks. Other questions? One of them that struck me, Grégoire, is that you put the QKD very much in the light of the bigger evolution of quantum internet, which is again a push that is many ways out. So in a way, you're embarking in 2007 on the QKD thing is sort of now being replaced. Are you indeed restructuring the whole, let's say, strategy behind that part? Is it going to be a new entity? It's going to be a new effort from IDQ next to your QKD effort, or do you see them as one whole and one journey into the future?
No, I think it's really part of our strategy. IDQ has, from the beginning, from day one, had two activities. One in single photon detection and tools, and the other one being QKD and QRNG application to security. And so with our activities in single photon detectors and other tools, we're very close to the research community. And so we want to work with the research community to bring the first next generation kind of quantum communication applications while deploying today's network. And one day, kind of the short story is that one day we'll take out trusted nodes and replace them with quantum repeaters.
Yeah, two sides of one strategy, and that's great to hear, great to hear. Any last question to Grégoire? If not, thank you once again, and thank you also for supporting this community, the way you do. Thank you.